In this lecture 2 of electrical fundamentals, we will study the resistors, the color codes related to resistors, variable resistors, conductance. We'll talk briefly about DMM, the digital multimeter, and we will also introduce you to the breadboard. It could also be a refresher in case you've seen it before. So a resistor looks in practice something like this. So these are actual resistors that we picked and we're showing it to you. So they are all resistors. One thing that you could identify is that they have different bands, the different stripes or different bands, and the bands they have different colors. These colors are there for a reason. They're not there just just for decoration, but they actually mean something. The bands essentially, if it's a code for us to read the value of the resistance. If you will, it's a bit kind of a cryptic way of reading the value of a resistance, and that's why we need to understand what these colors mean. They have a meaning, and we will show you how to read the bands in upcoming slides. So this thing here is essentially just the cover or the jacket of the resistor, and so it's just a piece of plastic. If you just you remove the plastic, that's the inside is actually the resistor. This is just a piece of plastic that is there to seal the resistor and also to show you the different color bands. Now inside the resistor you have, or basically what is the resistor? In it you have a carbon composite material, and this is the material that essentially forms the consistency or the resistance of the material. There are different materials that you could use. Any material that you use will have a certain resistivity, and we'll show you a table later on in this lecture. You also have the metallic parts to the resistor, and these are the leads. So you have one here and you have another one there, and you also have the insulation coating after around the resistance material. And that's basically, in a sense, kind of the inside of a resistor. There are different type of resistors. So some of the resistors will also be in blue, and this is another example where you could see the kind of the consistencies and the various components of a resistor that is made in blue. And of course, every resistor, when it has a different color or different bands, it will have a different resistance value, and we'll talk about how to assess that on the next slide. So here we will show you some of the basics of resistors that you should know. In terms of bands, typically you'll find 4 bands with resistors. These are the typical resistors that you could get off the shelf from stores. Sometimes you'll find 5 bands. These are military grade resistors. In here in this course, we will probably always stick to 4 bands. We will not use 5 bands, but if you see 5 bands, that's also a possibility. So it's important to know when you read the bands, the various bands, the color bands of the resistor, where do you start reading from? Do you start reading it from this side or from the other side? So it's the same resistor, except that we flipped it. And one thing that you should know is when you read a resistor, you always begin with like, so this would be the right answer. You always basically begin with the side that has the most concentration of bands. So in here, if you see one band, there's a gap, and then the highest concentration of bands is to the right. And this is not the right way of reading a resistor. When you read a resistor, you have to look at the higher concentration of bands. That's where you begin, and then you move to the one that is thinned in terms of in terms of bands. There's only one band after some gap, and so this is in fact the correct way of reading a resistor. And in here you have different colors. You have brown, black, red, and you have the gold band in here. So the other question that we should also ask is, do resistors have polarity? As you know, for instance, a diode, it has a certain polarity. If you put it in a certain way, the current will flow in it, and it would work. If you put it the other way, it won't flow, it won't work. So it has a polarity. Resistors do not have polarity. So if you have a battery, this is your plus, this is your minus, this is your plus, this is your minus. You connect it this way, where it's the thin band, the tolerance band here, and the others on the other side. Or if you flip it, you put the higher concentration of bands here, and then the tolerance after. With the plus, it doesn't make a difference. They are pretty much the same. So basically, what this leads you to believe is that resistance, they do not have polarity. You could connect them any way possible. The direction is really important just for you so that you'll be able to read the value of the resistance. But in terms of connecting it on a breadboard or soldering it, it doesn't matter which end you solder to what other end. The direction is only for reading the bands. The different bands that you see on a resistor, they have different colors, and the meaning of the color is explained in this table. So you have the colors here. We also write the text of the color because sometimes students could be colorblind and they cannot see the color. So we will also write the actual description of the color here, and the same thing with an exam. I will always give you this, not simply show you a picture just in case there's a confusion with identifying a color. You also have the digits that you have for each band, and you also have the multiplier and the tolerance. Now, how do you make sense of all this information on the table with a resistor? Well, you have to look at it in terms of bands. So as a first step, you need to place the resistor in the right way. So you'll know where is your first band and where is your fourth band. So we said that the higher concentration of bands should come first, then there should be a gap, and then there should be only one band. So in other words, this is the correct way of putting it, and we read in this direction, from the left to the right. So this would be your first band, this would be a second band, this would be a third band, this would be the fourth band. The first band is the first digit of the value of the resistance. The second band is the second digit. So the first band is, in this case, is brown, and brown has a value of 1. The second digit is the second band, so it's black, and black has a value of 0. The third band is the multiplier. So in this case, it's this one here. The third band is red, and it's a multiplier, and it's multiplied by 10 to the 2. 10 to the 2 is essentially 100. So basically 2 zeros are added to the value that you got here. And the fourth band gives you the tolerance. So it's here. So it's either, usually you will find either a tolerance of 5% or 10%. So it's either gold or silver, but there are other possibilities as well. Sometimes you won't find any value for that, and if that's the case, you also need to know that that means a tolerance of 20%. So for instance, if there is no color for the fourth band, that means it's a tolerance of 20%. Now, tolerance, what it means is that when you have these resistors manufactured by companies, you will never get the expected value. So the expected value or the nominal value or the average value is what you want. So let's say we want a 1K ohm resistor, and in fact, if you look at the bands, it gives you 1K, but let's say this specific resistor that you measure will be within a certain value. It's not a perfect resistor, there's a plus or minus to it. So that's what the tolerance means. So it's 1 kilo ohm resistor plus or minus 5%. And that's what the tolerance means. You will never get the exact one because of manufacturing errors and other things that could happen while producing the resistor. We'll see an example of tolerance later on, and I hope that will make a bit more sense. Another thing that I want you to realize is that if you have a resistor with values less than 10, so it's a small resistor, not a lot of resistivity, the third band, this one here, the third band, the multiplier, will either be gold or silver. It will be a small value. In other words, if it's gold, you will be multiplying by 10 to the minus 1, which is 0.1. If it is silver, you will be multiplying by 10 to the minus 2, or if you will, 0.01. So these are just something to also remember, that if you see 10 to the minus 1 or 10 to the minus 2, don't be alarmed. It is a multiplier, but it is a multiplier that will essentially shrink the value that you got, and that's why the value will be less than 10. So there's that to remember as well. In here, we will show you this example and we'll go in detail to figure out what is the value of this resistor. So again, we have the resistor, we place it in the right order. So from the higher concentration of bands to the thinned one band to the right. So we read in this direction. This is the first band, this is the second band, this is the third band, and this is the fourth band. So that's the first step. We need to put the resistor in the right order and identify which one is the first and all the way to the fourth band. Then what we need to do is we need to identify the colors. So this is brown, this is black, this is red, and this is gold. So brown, you come into the first band. So this is another table. It's kind of similar to the other table, except that now we created two columns for band 1 and band 2. Perhaps it's easier to read. So we're looking for the first band. So you come into band 1. You know the color is brown, so this is brown, and the value should be 1. So here we want to see a value of 1. Now, the next one is the second band is band 2, and it's black, so we're in band 2, and the color is black, so it's 0, and we will put a value of 0 here. The third band is red, so and the color of it, the color is red, and that's the third band. So this is the third band, and the color is red. So we multiply. That's why it's called a multiply. We multiply by 10 to the 2, and 10 to the 2 is essentially 100. Okay, and the fourth band, it is a gold color, and that's the tolerance band. So fourth band, tolerance band, gold color, and that's a value of 5%. So here, this gives us a plus or minus 5%. Now that we have this information, how do we put it all together? Well, 1 and 0 is basically just we put them together, one next to each other, so it becomes 10. And then 10, you multiply it by this value, which is 100. So 10 times 100, that becomes 1,000. And then you have your tolerance of 5%. So that's 1,000 ohm plus or minus 5%. If we were to write it in engineering notation, we would write 1 kilo ohm plus or minus 5%. And this is the value of this is basically the reading of this resistor. Okay, so we might say, well, what is this 5%? Like we said before, this is the tolerance. So there are manufacturing error that will happen, and that's why you will never get a perfect 1 kilo ohm resistor. If you measure it with a DMM, you'll see it's never 1 kilo ohm. It's either 1 point something or 0.9 something kilo ohm, but never 1 kilo ohm precisely. It's very rare that it happens, but it's always within a certain standard deviation or a certain margin around the mean. So now, how do we figure out this in terms of resistances? What is the range for the resistor? Well, you have to figure out 5% of 1 kilo ohm. So essentially 5% is 0.05. So you take 5, you divide by 100, that becomes 0.05. And you multiply 0.05 by 1,000, because this is 1,000. And the value that you get should be 50 ohms. So you could write this, or if you want, you could also write it in this format. So it's 1 kilo ohm plus or minus 50 ohm. It's the same thing as saying 1 kilo ohm plus or minus 5%. It's just the same thing. And if you want to find the range for this, well, you could just take 1,000 minus 50 and 1,000 plus 50. So essentially, the value of your resistance will be anywhere in this range. You expect the resistor that you will use will be anywhere in this range. Right, so it's either 0.95 kilo ohm or 1.05 kilo ohm, and that's what the tolerance is. So I hope you're able to go from you know an actual resistor to a number, and then to make sense of the number to know what it means. Right? This is what you get, and then to really make sure what is this specific resistor that you have, what is the value of it. Well, you could always test it. You could always measure it with a DMM, and that will let you know the actual resistance value of this particular resistor that you're holding in your hand, and you're expecting it to be somewhere in this range. Now, in terms of knowing the values, well, this is known as the minimum value of the resistance. This is known as the maximum value of the resistance. And this is known as the nominal value of the resistance, or if you will, the average value of the resistance. So far we saw resistors, but we saw that these resistors are specific values and they are in fact fixed. We cannot change the resistivity of this component, of this element. In here, what I wanted to show you very briefly is resistors. So these two, this one here and this one here, they are two type of resistors that are known as variable resistors. In other words, you have the liberty to in fact change the value of the resistance that the device will have, that this component will have. And the way you do this is by twisting or moving the knob that you have here, or using a screwdriver and changing it with this one here by changing by turning it left or right to change the value of the resistance. There are two type of variable resistors. There are one type of variable resistors that are known as rheostats, and there's another type of resistors that is known as potentiometer. They're both variable resistors, but they have different kind of functionalities. For with a potentiometer, what you're in fact doing, you are adjusting the voltage. So the voltage is being adjusted. And with a rheostat, what you are in fact doing, you are adjusting the current. And for different applications, you would use one or the other. So here we'll just show you an example of how you can use one or the other. This is basically just the symbol of it. So essentially it's just the symbol of a resistor, but now you have an arrow that goes in the middle, and as you notice, there are three terminals. This is another symbol. This is the symbol for the rheostat, and in fact, if you notice, the rheostat has exactly the same symbol of a potentiometer, except that one of the nodes is just connected as such. So you pretty much have two terminals as opposed to three terminals. So there's a short circuit in here. Um, and there's a description of it as you see in this image. Now, for the different functionalities of them, I'll just show you two examples here. So, for example, if you have a dimmer at home, you have a light in a room, and you're able to dim the intensity of the light. This dimmer that you're using, this switch that you are moving with your hand to dim or brighten the room, is in fact a rheostat. It has a rheostat in it, and it allows you to increase the level of the current, or to decrease the level of the current, right? And all of this is possible because of the relationship through Ohm's law. Right, so V is equal to Ri. We will discuss more on Ohm's law and the relationship later on. But essentially, if you keep the voltage fixed, then you will have a relationship between the current and the resistance. Right? Current is inversely proportional to resistance. So if you change one, you'll change the other, and that's how this relationship happens. A potentiometer could be an example of, let's say, a speaker. So you have a speaker, and the volume that you have changes the intensity. So essentially, you have a knob, and you could change the volume. You could either make the sound that comes from a speaker loud or less loud, right? So more quiet, right? And this knob that you're adjusting essentially is a potentiometer. It has the capacity to change the voltage, and again, if you hold the current constant, and then you will have a relationship between the resistance and the voltage, and in this case they are proportional to each other. So these are different ways that you could use a variable resistor. Variable resistor, potentiometer, rheostats, they are not really part of this lecture. They're not part of this course, but I wanted to quickly mention it to you just in case you see it later on, so you have some overview of it. And as we move in this throughout the different courses of Sheridan, you will take other courses where you will go more in depth with them, and you'll study the features and attributes, and you will in fact test them in labs. Now in this lecture, we're focusing mainly on resistors, and as we discuss resistors, we talked about the resistivity and what that all means. But what if you take the value of resistance, and instead of looking at it from a resistance point of view, you want to see it from its conductivity. How conductive is a material, not how resistive it is. It's kind of looking at it from a different vantage point. So in that case, if we're talking about conductance or conductivity of a material, you could always find it. It's the relationship between resistivity and conductivity is just 1 over each other. So let's say we give you a resistor of 10 ohm, and then we tell you what is the conductivity or the conductance of this device. You could just say it's 1 over 10 ohm, and that should be 0.1, and then it has a unit. The unit that we use for it is Siemens. So as you see here, there are 2 ways that you could represent the units of it. As we have with resistance, the unit of it is ohms. The units for conductivity is big S for Siemens, or otherwise it's also called mho. Written as MHO. So you could use one or the other. The one that I prefer that you use is the big S. The Siemens is more common. It's generally used in publications and so on. So I think you could certainly use this, but the other one is fine as well. So the question that one could ask is, so let's say we have a resistor, and we did talk about the consistency and how a resistor is built. So let's kind of give a model of how a resistor is put together. You do have the leads, so this is metallic, and you also have an electrical contact. So this is your an electrical contact here, an electrical contact on the other side. It just happens that in here it's square, but otherwise it could be of any shape. It could be circular, it could be other shapes. It doesn't really matter. It just happens that in this picture, in this model, it's a square, and A is really the surface area, the area of this box here that you see. And L is the distance between this electrical contact and the other electrical contact. So in other words, when you find the resistor really depends on the dimensions of your equipment, of this element that we call resistor. How big is it? How long is it? How wide is the cross section, the metallic area? And also, what is the material that you use to find this resistor? I mean, in this case, we see I've written to you a carbon composition, but otherwise, it doesn't have to be a carbon composition. What if you have somebody that puts, I don't know, a rubber or a piece of wood in here between these 2 electrical contact? I mean, it's odd to put these different things like a rubber or a piece of wood. We kind of know through common sense that they are not. I mean, we know that they won't let electricity go through them. They are absolutely not conductors, so they have a very high resistivity. So they're not very practical for electrical circuit, but I'm just trying to kind of give you a sense that you could in fact put whatever whatever substance you want in here, and different substances will produce different resistive elements. So just by the dimension of this model and the material that you put between these 2 contacts, you should be able to in fact calculate what R is. And the formula, and this really comes from physics, it's this. It's rho, this value here, this Greek letter rho, times L, the length between the electrical contact, divided by the area. The area is the cross section of the electrical conductor, the electrical contact that you have. In this case, it just happens to be this square here, and so basically it's the area of the square. But then again, it just depends on what is the model that is used for the resistor. Now, so maybe I could just show you the units for it. So L is, of course, it's a distance. So we have to use the SI units, the International System of Units. So we will use meter. And then the area is meter square. So it's meter divided by meter square. So you have a meter in the bottom. And on top, what you have is this thing here, which we call the electrical resistivity of the material. So different materials will have different resistivity. A piece of wood will have a certain resistivity. A piece of metal will have a certain resistivity. Gold will have resistivity. Silver will have resistivity. Every element that you can use will have a certain resistivity. So you want to use something that is appropriate for whatever we're building. Electrical circuits will have certain resistivity that are typical to them, but otherwise anything that you use in a circuit, including a wire, will have some resistivity. Wires are not ideal, they're not perfect, they will add some resistivity to the circuit. And so it depends on the type of wire that you're using. So the unit for resistivity is ohm times meter. And in fact, if you work it out, this is ohms times meter, this is a meter, right? So it becomes ohm times meter square, and this is the area, it's meter square, so it cancels out, and the unit that is left is ohms. So that really kind of gives you a sense of how you go from these different elements to the value of resistance in ohms. So I think that's a neat way to understand how a resistor is basically formed and how you could obtain a value for it. Now, what if you're interested by the conductance of a resistor? Well, conductance, as we said, is simply the 1 over of the resistance. So you simply do 1 over resistance, and the A goes on top. It's in the numerator, and then the L, the distance between the conductors, goes in the bottom. And here you could simply write 1 over rho, or you could simply use this Greek symbol sigma. Sigma is in fact equal to 1 over rho. So these two is the 1 over of the other, right? And the unit for this one, for the conductivity, is Siemens per meter. So if we could do we could check the units. This is Siemens per meter. This is meter in the bottom, so it becomes Siemens per meter square in the bottom. And on top you have meter square, so it cancels each other, and the unit that you will have for conductivity will be Siemens. So that's kind of how you could use one or the other. I just wanted to show you briefly a table that shows you the different values for resistivity. And by the way, all these values were measured at a temperature of 20 degrees Celsius. 20 degrees Celsius is considered the room temperature. And so if you look at a silver, it has a resistivity of 1.9 times 10 to the minus 8 ohms per meter. So in fact, it doesn't have a lot of resistivity. It's in fact a conductor. It's a very good conductor. Gold is another great conductor as well. So these are copper, gold, silver. These are all great conductors, right? They all have a very tiny resistivity, which means if you do the 1 over, they are they are strong conductors. Whereas if you look at quartz or maybe glass or rubber, they have a resistivity of 10 to the 13. A piece of wood is not, I don't think it's listed here, but a piece of wood has a resistivity of 10 to the 14 up to 10 to the 16. If it's a piece of wood that is a bit wet, it's a damped piece of wood, it has a resistivity of 10 to the 3 to 10 to the 4. So as we expect, a piece of wood, a rubber, it should not be conductive. It should be very resistive, and in fact, the resistivity of it is very, very high. So this kind of gives you a sense of how resistivity is for different elements. These are values for rho. If you were interested to find the values for the conductance, you simply take the value and you do 1 over this. So if you want to find, I don't know, the conductivity of silver, you would do 1 divided by 1.59 times 10 to the minus 8, and that gives you the conductivity of silver. So that's just something that you should realize. There are different equipments that one can use to measure the value of resistance. So we saw that we can certainly determine the value of a resistance by simply looking at the size and dimension of a resistor, and that gives us a model to assess what is the value of the resistor. We also saw that we can determine the nominal value and the tolerance of a resistor from the manufacturer by looking at the color stripes. At this point, what if you're curious about the specific resistor that you're holding in your hand? It's not the nominal one, it's not the tolerance. I mean, that's interesting, but you really care about this specific resistor that you're holding in your hand, and you want to know what is the value of it. So you can certainly find this with tools, with different tools to do this. Now you have this tool here. This is known as a VOM, or a volt ohm milliammeter. As you notice here, you have a needle and then you have a reading that you have. And this is, of course, an analog display. So it's not digital. You don't see digits properly like this one here. You also have a DMM, a digital multimeter. And we have DMMs in the labs. So whenever you go on campus and you go to the lab area, you'll notice a fancy DMM that we have with up to 6 significant digits. So that it's even better than this one here that you see. This has 4 significant digits. You'll see 4 digits. So 4 significant digits. It's of course a digital and a digital multimeter. In the shorthand way of calling it is simply DMM, and it's certainly way better and more precise than this one. This because it's analog, it's hard to read. There's also a human factor in it, so you might read it wrongly. So certainly this is highly encouraged to. You are highly encouraged to use a digital device as opposed to an analog. The only kind of thing to realize is this one is always cheaper, significantly cheaper, sometimes even in the five Canadian dollars that you could in fact find it in dollar stores, whereas this one it's usually more expensive. So somewhere between $30 if it's on the lower end, it doesn't have all the features, and perhaps up to 70 Canadian dollars. You could buy it in all these stores that we have, like Home Depot, Canadian Tire, Ronan Entrepôt, and other places. So they have these different devices. And I guess if you're curious how to do the measurement, well, you put the arrow, put this arrow, you turn it as you put it to the omega, the symbol omega, and that will allow you to read resistance. You put the common here to the black wire in here, and you put the red one in here where you see the symbol omega, and then you simply put your leads to the resistor, whichever end, and that's going to give you a reading of the resistivity, or not the resistivity, but rather it will give you a reading of the resistance of your device. So that should be an interesting way to in fact realize the specific unit that you're holding, what is the value of its resistance. There's a big chance that you've already seen this in perhaps high school or other courses. Breadboard. So breadboard, as the name suggests, originally it came from the actual breadboard that people use in their kitchen to cut bread or to prepare food and so on. And it was used as a surface, and then electrical components were mounted on top of it. And so that's kind of the genesis of what breadboard is. But for electrical engineers, a breadboard is really this device here. So this is what we mean by a breadboard if you talk to an electrical engineer. This device is pretty cheap. You could certainly find it in an affordable way, so perhaps somewhere around 10 Canadian dollars to buy it. It does fluctuate once in a while, but in general, this is the rough price for breadboards. They exist in different shapes and formats and sizes, and you have smaller ones, you have medium ones, and then you have larger ones. And you could certainly attach breadboards together. So you could have a bunch of breadboards, and then you could attach them together to form a bigger area to build, to have more freedom to build a reasonable size circuit for prototyping or whatever you're doing. So you simply get a breadboard like this, and then you see these connectors here, these plastic connectors. So this allows you to connect a few of these breadboards together to get a bigger area. And with multiple breadboards connected together, then you have greater surface to do whatever you're trying to do for your prototypes. Now, some of the key advantages of breadboards are listed here. So they are useful to build a circuit very quickly on the fly. So you do not need to solder electrical components. You don't need to do that. It's very flexible. You could right away, if something doesn't work or the result that you get is not as you expected, or there's something wrong in your analysis or in the setup of your circuit, you could certainly remove components, adjust everything, and then test it again on the spot. It's just kind of plug and play, if you will. Whereas if you were to solder, then that's a problem. I mean, if you solder a circuit and nothing works properly, and there's the connectivity wasn't done in the proper way. Then you have to remove the soldering, and then you have to analyze and see what's going on, and then do it again. So that's not very convenient. So Breadboard adds this convenience to designing, and to specifically during prototyping and during testing. It's very practical. It certainly is very practical for student projects because right away you could test different configuration and come up with a good alternative. So one approach would be to perhaps simulate, run a circuit on using a simulator such as Multisim or Spice or other type of soft circuit simulators. And then after simulation, then perhaps you could build it using a breadboard, and if everything is fine and you're happy with the result, then you could print a PCB, a printed circuit board of what you're doing. So there's different steps in converging to a product that you're trying to come up with, a prototype, and these are the typical steps. So Breadboard is always in the loop of what you're doing, and it's a great tool that you should get familiar with. Now, one of the problem with Breadboard is that quite often students they're not quite sure how the connectivity of the breadboard is done, and therefore they just connect things and then it just doesn't work. So I think it's really important to understand how a breadboard works. Sometimes I do encourage students to perhaps take apart a breadboard to see it physically with their hands how a breadboard is formed. But if you don't want to break yours, usually in class I take apart my own breadboard so you could get a sense of how everything works. In here, we're not in the lab, so I'm going to just show you the inside of the breadboard with a picture. So this is a drawing of a breadboard, and we want to basically see the inside of it. I think a good way to understand how a breadboard is formed is through the pictures here. So this is your typical breadboard. You remove the plastic on top, and then you will find these metals, right? These piece of metals. These metals, they are referred to as channels. So this piece of metal, the long one here, this very long one, which kind of is represented by this line here, this other line here, these columns, this column, this column. So you have 4 of them. They are essentially all connected together, just one piece of metal. So if you connect any component to any of the holes, then you're pretty much connecting all of them to one node. They're all connected to the same node. The same thing applies to this one and to this one. Now these, for instance, this one here, this red one, that is typically for the positive value of the voltage, and the blue one or the black one that you have next to it, they are a full channel that is connected to fully, but between each other they're not connected. They are not connected between each other. So this is something that you should know. The other ones that you have, the rows, so for instance from A to E or from F to J, these are different rows, right? The entire row is connected together. The entire row is connected together. In fact, you have a picture of it here. You have one hole, a second hole, a third, a fourth, and a fifth. So you could in fact pin a component to these holes, and you have to push it a bit hard, not quite hard, but you just push it so that it enters this metal and it stays firm on your breadboard. So in here it's called a 5-hole channel. It's a channel, it's all connected together, just one piece of metal, and anything that is connected here means that everything is connected on a same node. But then every row with the row above it or below it, it's not connected together. So if you have multiple rows and you want them to connect together, then you'll need to put a jumper. So that's a very nice figure that kind of gives you a sense of how a breadboard works. So this is, in this picture, you have it. It tells you the entire node. So this is one big node. It's all connected together. This is another big node. It's all connected together. The same thing on this side as well. The rows, these are all, each of them is a node. It's a node, it's a node, it's a node, but then it's not connected to any other node. If you want to do that, you need to put a jumper. Okay, so we'll see a very basic example with one resistor and an LED. I'll just show it to you, and then we will just show you how the inside of the breadboard is expected to connect. So in here, what we have is the following. You have a basic circuit, and essentially what we have is we have some energy source, this DC source. You could think of it as a battery or a chargeable battery. It has 2 wires. It have your positive and you have your negative. The positive comes in here. I think it's always good to stick to the convention of the board. So anytime you see basically when you want to connect a source, always use the extremities. Right, so you have a big line here, a big column for red, which is for the positive, and a big column for blue. And you also have a big column for red and also for blue for negative. So just stick to it. Just use that. Let's build the circuit in a nice, clean way. So you could put a positive here. It is connected together. So this is all connected together. At this point, you could take a jumper. You could take a jumper, a wire, a short, small wire. And this jumper is essentially connected to this because they're all connected together. You bring it to this column. You bring it to this, to this row. Okay, so now you have this red line from the inside is connected. It comes to here, and this row is connected together. So you could in fact pick your LED anywhere on this row. So you put it in here. You have your LED. You pin it on the other side of the row. So this side is now pinned. So now you have your wire. It comes in. It's all connected together. It's here. It's connected together underneath. You go to the LED, and then it's connected together on this row. You connect a resistor. Connect the resistor from the row to the negative side. This entire thing is connected together, and you go all the way to your source. So now you really have a path, a closed loop for your circuit. So if we see it, this blue line is kind of my drawing just to kind of show you what happens inside. Then you have another one that is here. You have another one that is here. You have another one here. And as you notice, your current would flow properly in this path. There is 100% a closed loop, and therefore it's a functional circuit. So that's kind of a basic example of how a breadboard works. Hopefully you'll get the opportunity to play with this in the lab to get a better sense of how it's done by actually practicing it with different experiments. So these are some key terminologies and definitions. I'm not going to go and read it. If you're interested, you could pause the video and read them. We did discuss it throughout the lecture. So we have a series of questions that we could solve together just to get a sense of how we can better understand resistors and how we could go from the color codes of it to a value or the reverse. So let's do these problems together and let's see if we can find the solution. I did put the table for the resistors. In general, we do prefer that you memorize it, but if you can't, that's okay. In an evaluation, there's a high likelihood that I will give you this table, so you don't need to spend time to memorize it. I'll provide it to you. But if you do memorize it, that's even better. It should go way faster. So the question is now, what is the nominal value of a 4-color resistor? So right away we know we're talking of a resistor. It has 4 color bands, not 5, but 4, with the color bands gray, red, black, gold. Gray, red, black, gold. And we're looking for the nominal value. So nominal value is essentially the average value, the expected value, or the nominal value. They all kind of mean the same. So when you have a value of a resistor and you read it from the bands, you'll get the nominal value plus or minus the tolerance. So at this point, we don't really care about the tolerance. We just want the nominal value. But let's nonetheless get it, and then we'll move along accordingly. So if you see here, this is gray, right? So this thing here is gray, and let's look for gray. Where is gray? So this is the first band. So we look at band 1 and we identify gray. So gray is here. So it would be this value. Value would be 8. So we have an 8. The next one is red for the second band. Second band is here, and we look for red. Red is here, and the value for it is 2. So the next one is 2. So we could enter 2. And the third one, the multiplier is black, the third band. The third band, we're looking for black. So black is this one here. It's times 10 to the 0. Times 10 to the 0 is essentially 1. So you simply multiply by 1. And then you have gold for the fourth band. So this is the fourth band, and we're looking for gold. This is gold. So we have a tolerance of 5%, plus or minus 5%. Okay, so if we look at this, it's 82 times 1 plus or minus 5%, which basically means it's 82 ohms plus or minus 5%. We are interested by the nominal value, And therefore, what this means is that the answer will be only this part here. Only this part here, right? The 82 times 1, which is essentially 82, and the answer should be B. Okay, so the answer should essentially be B. Let's see if that's what we got, and that's exactly what the answer is. So you see how we do it gradually, and how we converge to the answer. Let's do another one on the next slide. So in here we're told that we have a resistor. The value of the resistor is 330 kilo ohm, right? There's a K here, don't forget that, the kilo ohm, plus or minus 5%. So the tolerance is 5%, 330 kilo ohm is the nominal. So this is the resistor, and we're asked what is the color bands that would match this value that were given to you. So here we're kind of doing the reverse. Usually the way we do it is we show you the resistor, we show you the colors of the bands, and then we tell you to find the value of it. Now we're giving you the value, and we're telling you to do a reverse engineering, is to find out how would the resistor look like. So you take it apart. Gradually. So we could essentially just take it one step at a time. So this is 3. The first digit is 3. So we go to band 1 and we look for 3. So 3 would be color orange. So it would be color orange. So this is orange. This would not work. It's not red. It's not yellow. It's not yellow. In fact, right away, just by finding this, we identified that the answer would be B. So through the process of elimination, we realized that the answer is B. But let's nonetheless continue and try to find the others as well, just to make sure we did not do any mistake in here. So the next digit is also 3. So you go to the second band and you want to identify 3. This is 3. And the color of it is also orange. So the second color, we also expect it to be orange. That's the only one that has orange. So it's not this one. Certainly not this one, and it's not this one. So this is also still correct. And then we want to identify the third band. The third band is the multiplier. Now here, be careful. So usually when I show this to students, they tell me the multiplier is 10 because there's a 0. But don't forget that you are using also the prefix, the engineering prefix here, K, so the K and the 0 together, it means it's 10. The 0 is basically 10, and the K is 10 to the 3. And so when you multiply them together, 10 times 10 to the 3, that's essentially 10 to the 4, right? 10 to the power 4. So that's 10 to the 4. So if we look at the multiplier with 10 to the 4, it would be this one here, and this has a color of yellow. So the third one should be yellow, and this is still correct, yellow. So it's not brown, it's not red, and it's not green. Let's continue. And the last one is gold. So your tolerance is gold. And this is kind of, we've seen this before. Gold is here. This is the fourth band. So we're expecting a 5%. So it should be a value of 5%. I'm sorry, the way we did it is wrong. So we should come here. We see a value of 5%. So we're 5%. And we notice that the color is in fact gold. So this is gold. This is also gold. So this is correct, but everything else is wrong. So it's not A. This is gold, so this is correct, but everything else is wrong, so it's not C. This is gold, this is correct, but everything else is wrong, so this is not D. The answer is really B, right? So we did converge to the answer, and as you notice, it is B. So I hope you're able to kind of see how to go forward from a resistor to a value, or from a value to a resistor. So in question 3, we ask you, what is the unit of conductance that is used? So we know that conductance is related to resistance. It is in fact the 1 over the reciprocal of resistance. So conductance is equal to 1 over resistance, or resistance is equal to 1 over conductance. So let's kind of go through the process of elimination, which is perhaps the most powerful tool with multiple choice questions. So is it ohms? Is ohms the unit for conductance? No, ohms is the unit for resistance, so certainly it is not ohms. Is it coulomb? Coulomb is the unit for charge, so you know this from physics, and so certainly this is not the unit for conductance. Is it amps? Ampere? So it's not amperes, right? Amperes or amps, these are it is basically the unit for current, not for conductance. And the correct answer is Siemens. Siemens is the unit for conductance. So 1 Siemens is in fact equal to 1 over 1 ohm. So if you have an ohm, you flip it, that becomes a Siemens, a unit of Siemens. So we expect the answer to be C. Finally, we have this question, question 4, and in this question, what we're asking you is, what is the resistance and the tolerance of each of the 4-band resistors? So we give you a bunch of resistors, and we show you the colors for the bands, and then we tell you to find the value for it. The value, as we notice, it is based on the nominal value plus or minus the tolerance. So we could do it by looking at it like one step at a time. So let's check for A. A has a green. So green is what? If you look for the first band, is green. Green is here. So the value should be 5. So for A, it should be 5. Then it has another value, brown. Brown for the second one. So brown is 1. So it should be 51. And it has a multiplier of red. Red is times 10 to the 2, which is times 100, times 100. Okay, so 100. And it has the tolerance, which is in gold. So gold is 5%. So we could do plus or minus 5%, plus or minus 5%. And therefore, what we expect is the value here. So the nominal value, if you multiply it together, you'll get 5,100 or 5,100. And this is not in engineering notation, so you could write it in engineering notation. The value will be 5.1 kilo ohm plus or minus 5%. So this is the value that we expect for the first resistor. So 5.1 kilo ohm plus or minus 5%. For the second one, we could do something similar, and again we follow the same process. So the first one is gray. Gray is 8, so it's 8. We will have 8. The next color is red. Red is 2, so we could have 82. And the third band is yellow. Yellow is times 10 to the 4, times 10 to the 4. So that's 10,000 times 10 to the 4. And it has a tolerance that is silver. Silver is plus or minus 10%. Plus or minus 10%. So if you were to represent this in engineering notation, it would be 820 kilo ohm plus or minus 10%. This is what we get for the second circuit. So this would be the answer for A. Oops, sorry about that. The handwriting is very bad. I don't have a stylus. I'm just using a mouse. And this would be the answer for the other one for B. This is for A. So this is 5.1 kilo ohm. The other one is 820 kilo ohm plus or minus 10%. The third one is we have a yellow. So the yellow would be 4. So there's a 4 in here. There is this one here, the violet. Violet for the second band is 7. So it's 47. The third band, the multiplier is black. Black is 10 to the 0, which is basically 1. And we have a silver, so plus or minus 10%. 10%. So this is what we get for C. So 47 ohms. 47 ohms plus or minus 10%. Okay, so this is what we get for C. And finally, we could go ahead and determine the one for D. The first band is brown, so brown is 2. No, brown is rather 1. We have 1. The second band is black. Black is 0. The third band is gold. The third band is gold. So gold has a multiplier of 0.1 times 0.1. And the fourth band, the tolerance is also gold, which is plus or minus 5%. So 10 times 0.1, that becomes 1 plus or minus 5%. So it's 1 ohm. Don't forget to write your units, ohm, and that's what we get for D. So again, let's recap. The first one is 5.1. So again, the writing is really bad here, but I hope you got it. So it's 5.1 kilo ohm plus or minus 5%. The second one is 820 kilo ohm plus or minus 10%. The third one, C, is 47 ohm plus or minus 10%. And the fourth one is 1 ohm plus or minus 5%. So let's just check if the results are as such. 5.1 plus or minus 5%. This is correct. The second one is 820 kilo ohm plus or minus 10%. The third one is 47 plus or minus 10. And the last one is 1 ohm plus or minus 5%. So this is how we got it. I hope, despite the bad handwriting here, I hope you understood some of the steps of how we could determine the values, and you kind of understood a bit about some of the basics of resistors. Next lecture, we will cover Ohm's law and power and energy. Thank you for your attention.